One challenge that we have is that text is categorical. Text, they are not numbers. So, and our LLM is a it's our LLMs, which are neural networks, they they love numbers. They love numbers. So we would need to represent these words into what are called continuous valued vectors. So continuous valued vectors, it just means there are continuous numbers in the vectors, valued vectors. So we convert our words through some process into these continuous valued vectors. This process, it is actually called embedding. And it just doesn't apply to words only. The process of just converting any data into continuous valued vectors is called embedding. In our case here, we're just discussing words. Um, what we can do to do this embedding is we can use a specific neural network layer, or let's say what we're going to see in our model. We can have a layer that is dedicated to doing this embedding, or we can use a separate network. We can get another separate network that does that is good at creating these embeddings. It's created in good at doing these embeddings. And if you have used OpenAI before, you might have seen a model called Text Adder. I think it's called Text Embedding. Text Adder. Let me. I think it's called Text Embedding. I'm actually I haven't crammed the name, but yeah, I think it's called Text Embedding Adder 002 or something like that. It is a model that is dedicated to to create embeddings. That's all it can do. Create these continuous valued vectors. And it is a pre-trained it is also a pre-trained neural network. We can embed data which can be in the form of text, these words, video, or audio, and each one of these will have its dedicated model that does embed the embeddings. Multimodal models are beyond the scope of this book, but you can read up on how they do it. They have sections that are dedicated to embedding text, embedding audio, embedding video, and they use different techniques to fuse the embeddings. So and some of them they have different ones. They are, I think it's called cross attention. For example, in the Llama model, it is a cross attention fusion model, fusion method. You can read up on the different fusion methods because, of course, the text is going to be embedded differently to video and audio because they are different. They are different data types or data formats. But but yeah, the core of the idea here is we want to convert data, in our case, word from the distinct words, you see, distinct word into a continuous valid vectors. That's what we want to do. So the primary purpose that's pretty much just the primary purpose to convert non-numerical data into a format that neural networks can process. The most popular ones are word embeddings, meaning they're embeddings developed at the word level, but we also have sentence embeddings, paragraph embeddings at the paragraph level, or even document embeddings. And document embeddings. These ones are most popular for RAG when you're doing retrieval augmented generation, um, where you have your documents that are chunked in a database in a vector store somewhere. Usually chunk at the sentence level or paragraph level to create those chunks, and you do retrieval augmented generation. Not going to really discuss it here, but just know these are popular there. But for our case, we are going to do word embeddings because we want to train these GPT like LLMs, which actually do prediction of one word at a time, one word at a time. So to really do that, it's best to use word embeddings. Over the years, many algorithms have been developed, though. We have one that is very popular. Maybe you might have seen it called word to vec, which is just a neural network that was trained to generate these word embeddings by predicting the context of a given word, of a given word, given the target, given target word. So it's just it's a given target word. So the main idea is that words that appear in similar contexts tend to have similar meanings. That is the main idea behind word to vec. So, for example, if I'm to plot only two dimensions, so this is the second dimension and this is the first dimension. I'm plotting only two dimensions for it to be easy to visualize. Our brains are not built to visualize thousands of dimensions, but if we are to plot on two dimensions, words that have similar meanings, we hope that they are grouped close together. So here we could have Germany, could have Berlin, could have London, could have England. And what is interesting is Berlin is to Germany as London is to England. So you can start doing some mathematics. If you do not know what the capital city of England is, or you do not know what that London is the capital city of England, but you know Berlin is the capital city of Germany, after embedding your words or your these words here, what you can do is you can do some mathematical operations that say Berlin to Germany, or you can subtract the vector. You can subtract because yeah, this is just a vector, right? This is a vector. So these are all vectors. So you can do Berlin minus Germany. It should be equal to London minus the one that you do not know. So the one that you do not know is equal to London minus Berlin plus Germany. And these are you're not adding words or something. You're adding their vector representation. So these are numbers. And then you find the coordinates of this one here. And when you find the coordinates and you go there, you find that it is England. So you start doing some of those mathematical operations, which is exactly what you want in a neural network. That is why we have to embed our we have to embed our words so that we can start doing some mathematical operations on those words, which is what we'll see later on when we start doing some matrix operations on these words, because that's how the neural network is trained. It is trained through mathematical operations. So I'm just going to try remove this because I want to show some other examples as well. I think that is just okay. That should be fine. So some other words that are similar could be you could start having things like eagle, eagle here. That's an eagle, and you have a duck, and here you can have a goose. These are similar types of animals, and next to them, although it's an animal, but you can have a squirrel out there, out here. It is an animal. It is close to the animals, but not really like these animals that are like birds. And then and on another part, you can have these words that are similar, like longer, longest, and long. Also grouped together because they are sort of like similar. They're very, very similar. So that is the main idea of word embeddings, of especially for word to vec. That words that appear in similar contexts tend to have similar meanings. So when they are projected on this 2D space, for visualization purposes, similar words are sort of clustered together. These word embeddings, they can have varying dimensions. They can be from one dimension if you want to thousands of dimensions. Of course, there's going to be a trade-off. If you have one dimension, you can't really separate these words, as you can see. On two dimensions, still it is difficult to really separate, especially when you have billions and billions of tokens, or let's just say you have millions of words. Yeah, we have millions of words in different languages and all of that. It might be difficult to really separate them out and come up with some mathematics that actually works if you have very few dimensions. But at the same time, when you have higher dimensions, it becomes computationally expensive for you to do some calculations on them because now you're dealing in thousands and thousands of dimensions. Typically, large language models, they do not use this word to vec. They have their own, they have their own, they have their own embeddings. They have their own embeddings that are part of the input layer. When you input it, it has a layer that does the embeddings, and that layer, that embedding layer, it is trained during training. So it is optimized during training. We are optimizing the way this model embeds words, because at the end, it's going to give you an error term. Maybe the error is because this we are not embedding correctly. So these embeddings are all this embedding layer. It is also optimized during training. The advantage of doing this, of optimizing the embeddings as part of the large language model, is because it then, without and not use something like word to vec, is that the embeddings are very optimized and specific for that task, for the task we have, and the data we have. Then the data we have. So they are very bespoke like that, which makes it very, very good to actually embed them in the LLM, and it improves the performance of the LLM. For GPT-2 and GPT-3 models, the embedding size and dimensionality of these models, they vary depending on the size of the model. For example, for GPT-2 models, the small models, there's one with 117 million parameters and one with 125 parameters, 125 million parameters. These two use 768 dimensions. You see what I mean when I say difficult to visualize? That's why we just put two dimensions there. So this embedding, the embedding layer for these two models, they embed in 768 dimensions. Then the large ones for the largest one for GPT-3, which is a 175 billion parameter model, this one, it has 12,288 dimensions. So a word like Houston, what that pretty much means is a word like Houston, sorry, a word like Houston, it is represented in a vector that is numbers, that is 128,200, 1,000, 12,228 numbers in it. So the Houston is converted into a vector with 12,228, 12,288 numbers, which is the dimension. And if I was using GPT-2, the 178 million parameter, the vector itself, we have 768 numbers in it. We're going to see what I mean, like the numbers that represent my name, Houston. We're going to see that later. So now we've discussed the high-level details of what embeddings are. Now that we know embeddings, we are going to say, okay, but we are probably not going to use the whole word like Houston. We might split it into different tokens or different parts. And so that is the discussion for the next video. We're going to look at what it means to do tokenization.